Now moving on, here is another example in which we have to prove an inequality with the help of induction. Right, so let's see here. Prove that n square is greater than 2n plus 3 for n which is greater than 3 and n is a natural number. So now here if you observe, as compared to the previous examples, the n does not start with 1, which is a usual natural number to start off with, but here it starts off with actually 4. That is the least value of n that we have to consider is actually nothing but 4, right? So let us consider it for the smallest case. So that means here our step 1 will start off with the smallest value of n as 4. Now if you consider the left hand side, that is nothing but n square, that is 4 square, which is equal to 16. And if you consider the right hand side, by putting n equal to 4, so that is 2 into 4 plus 3, that turns out to be 11, and we see that clearly 16 is greater than 11. So therefore p of 4 is true, right? So that's the first step. Now in case of step 2, we assume the truth of p of k, where, just to recap, k is some arbitrary number between which is greater than 3 but which is less than n. So it's like some arbitrary number in between, but of course it has to be a natural number only. So if we assume for the time being that p of k is true, that means what we have assumed essentially is k square is greater than 2k plus 3, correct? So this is our assumption. Okay, now what we have to prove is p of k plus 1. That means what we have to prove is, in place of k, let us substitute k plus 1. So we have to show that k plus 1 the whole square is greater than 2 into k plus 1 whole plus 3. So that is, we have to prove that k plus 1 the whole square is greater than 2k plus 2 plus 3, that is 2k plus 5. So basically this is the inequality that we have to prove in order to complete the induction. Now let us start off with the LHS, that is, here we know that k plus 1 the whole square, we know that that is equal to k square plus 2k plus 1. But what we have just assumed is k square is definitely greater than 2k plus 3. So that means if we substitute that here, we can definitely reason out that k plus 1 the whole square has to be greater than 2k plus 3 plus 2k plus 1, isn't it? Because k square itself is greater than 2k plus 3. So that means what we have got is k plus 1 the whole square is greater than. Now let us look at the right hand side that we have to adjust in the inequality to be proven. Now here we have to show that the right hand side has to be 2k plus 5. So therefore from the required expression, the expression that we have obtained at the last step here, we extract 2k plus 5, that is we express it as 2k plus 5 plus, see, the remaining 2k will come as it is, and we had the constants as 3 plus 1, that is 4, so we must subtract 1. Okay, now in order to prove that k plus 1 the whole square is greater than 2k plus 5, which we have got as expected, we must show that the remaining quantity has to be positive, because if it is negative then it may hamper the inequality, correct? Now to prove that 2k minus 1 is greater than 0, just take a look at what is k. Basically, as we saw, k is some number which is greater than 3. So that means if k is greater than 3, so clearly 2k has to be greater than 6, and therefore that means 2k minus 1 has to be greater than 5. And if 2k minus 1 is greater than 5, that automatically means that 2k minus 1 is a positive number. So therefore the second term is a positive number. So therefore we have effectively proven the required inequality as required, right? So therefore combining steps 1 and 2 results, we conclude that the given inequality is true for any value of n which is greater than 3.